Hi there, this is Edward from Enfield Physics Tutor. Today I've got a short video for you on how to examine the motion of a projectile as you fire it out at various different angles to the horizontal. We use Excel, and I have to say I really like this investigation and I hope you find it useful. Let's define our positive directions with a normal X and Y graph. Place our ball at the origin and it's going to shoot off, as we know, in that direction at an angle of 60 degrees to the horizontal and with a magnitude of 7 meters per second. Now we'll know it's going to follow a parabola, so let's pull out just the vector, redraw the X and Y axes, and now we can look to get the components of the original velocity. So the reds show these, Y and now X. So from trigonometry we know that V in the X direction is going to be 7 cosine 60. And that V in the Y direction is going to be 7 sine 60. And those are our initial velocities in the X and Y directions. So here's the top of the spreadsheet, and you can see that we're going to have our various variables here. I want to draw your attention to G, which is negative in this sheet, and that's because we defined the upward direction as being positive. The angles in degrees, I made a note of that because, as you'll see, for the formulas for the initial velocity components, we have to convert the angle into radians. Excel needs radians, and you can see it happening there. Now, if the angle is 0, you'd expect there to be nothing in the upwards direction, and there isn't. Let's see what happens if we put an angle of 45. They should both come out as the same number. And indeed they do, as I'm sure you know, the sine of 45 equals the cosine of 45. And in our case, we're timesing them both by their initial velocity of 7, hence the number 4.9. Now let's look at the equations that we'll use to work out our values for displacement in the X and Y direction. So for the Y, it's S equals ut plus half at squared. For the horizontal displacement, we've got to remember that Vx is actually constant, it's not going to change. That makes life really simple. We just use distance equals velocity times time. Back to our Excel sheet. See, we've got 3 columns now for T, X and Y axes. And we're going to start off with our initial conditions of 0, 0, 0. So let's deal with the T column first. We're going to go up in steps of dt, which in this case is 0.1. So we simply just get the previous cell value and add on whatever dt is set to. Make sure we put hash symbols into that reference to keep it fixed, and now just drag down, and there's our time values for the moment. Now it's time to look at the X axis. Remember, we said that this was simply going to be a case of multiplying the initial velocity, which is the cell K2 at the moment, and make that a fixed reference. Press F4 to get the dollar signs, and then multiply that by the value for T, which is that column there. Hit return, drag the formula down just like before, and you can clearly see there that the T columns, or the X columns I should say, is going up in regular steps. Now we look at the Y axis. Now I just want to remind us about the formula we're going to use. The vertical displacement is going to be S equals ut plus a half at squared. So let's transfer that formula into Excel. First of all, select the initial Y velocity, add your dollar signs so that it's fixed, and then multiply by the time interval. That'll be the ut bit. Now we add the plus sign to do the half, which is right 0.5. Going to times that by acceleration, which of course is g. Don't worry about the minus, we need that minus sign because negative is downwards. And now we have to times it by t squared, which I did the lazy way by timesing the t interval by itself. There we go. Now we can drag down, and there are our values for Y displacement. So you can see for an angle of 45 degrees that the Y value goes up, becomes positive as the ball gets higher, then it goes back down to 0 as the ball comes back to its original height. And you can see the last value there where it's t 1.1, the value for the displacement Y has just become negative. So this is like we're throwing it off a cliff and it's just starting to go down lower than the initial point that you threw it from. We've generated about a second's worth of data. It's not really enough, so we just highlight the bottom row and drag it down to give ourselves getting on for 3 seconds worth of data. That'll make the graph look a bit more complete. Now in order to draw the graph, we just highlight the 2 columns for X and Y, and it's off the top of the screen there, but it's just insert a scatter graph, an XY scatter, and there it is, and you can see wonderful parabola shape. So I'm just going to resize that, make it as big as I can on the screen, and then I'll show you a few nice little things you can do with it to analyze projectile motion. So there we go, that's our original graph there. Now we can make the time interval a bit smaller, so let's move it to 0.05 of a second as compared to 0.01, and see how brilliantly it's redrawn with a load more points. Beautiful smooth curve, as you'd expect. At this point I want to clarify what it means that the graph has gone into the negative section of the y-axis. So in effect what's happening is this is as if we've thrown the ball or whatever it is from a height, like off the top of a tower block or a cliff or something, and so the ball goes along, and after about 2 meters in the x direction it reaches its peak, and then it falls back down, and after about 4.3 meters of travelling in x direction it's back at the same height from which you threw it. After that it proceeds to fall down further down towards the ground, kind of into the negative section, i.e. below where you threw it. Well, that's all fine and dandy, but I'm going to select the y-axis and then use the format axis toolbox to make the minimum value for y equal to 0. That way we lose the negative section. Now this is effectively like throwing a ball from ground level and then seeing how it moves until it hits the floor back at ground level. We'll start off our little investigation then by setting the angle to 60 degrees. And you can see the ball travels in the parabola, as you know, hits the floor at around about 4.3. Now let's change the angle. This time we have an angle of 10 degrees, and you can see that the ball is hitting the ground much sooner, this time only about 1.8 meters. Next up we'll try 30 degrees, and now the graph shows that the ball hits the floor at 4.3 meters. Next up 45, and it's crossing the axis now at 5 meters. Now we'll go to 60 degrees, 4.3 meters, and now one more at 80 degrees, and the graph shows us that the ball's hitting the floor at about 1.7 meters. These results clearly show that if you want to throw a ball the furthest distance and you're at ground level, you need to throw it at an angle of 45 degrees. Thanks for watching.